Now we can turn to the k-nearest neighbors algorithm. We've already seen the nearest neighbors algorithm in action when we looked at the construction of Galton's predictions for the height of a child based on the mid-height of the parents. To predict the height of a child whose parents had mid-height equal to 68 inches, we might use the mean of all children born to parents with mid-height within 0.5 inches of 68 inches. This seemed like a reasonable approach in Galton's context, but things break down in a bad way when there are more predictors. To see why this is so, consider a dataset in which the mid-heights of parents span 10 inches, so that an interval of 0.5 inches on either side of the center is 1/10 of the range of possible values. We can break our range in 10 equal pieces, and each observation can be placed in the piece containing it. If we had 1,000 observations, some pieces will have more points than others, but most pieces will have many observations. Now, think what would happen if we had 2 predictors and broke each predictor's range into 10 pieces. Then we get a grid of 100 boxes. Some boxes will only have a few observations, though on average each box will have 1,000 divided by 100, or 10 observations. We have an average of 10 observations that are close to any pair of predictor values, in the sense that they share similar values of both coordinates. But what happens as the number of predictors goes up? If there are 3 predictors, then there are 10 cubed, or 1,000 boxes, and an average of just 1 observation per box. Things get even worse as the number of predictors gets larger. The problem is that most points are different from the others in high-dimensional space. This is called the curse of dimensionality. Rephrased in common language, it says that if we use many different measurements to classify people, then every person looks very different from everybody else. In that case, it's hard to find patterns to help us make predictions. There is a simple way to modify the nearest neighbors algorithm to deal with this problem. Instead of insisting that similar observations have all their predictors close together, we just measure the distance between 2 observations using the Pythagorean formula, the square root of the sum of the squared differences of their predictors, and use the closest observations to make our prediction, even if those observations aren't all that close to the new observation we're trying to predict. The k-nearest neighbors algorithm uses the closest k observations to make predictions. When predicting a numerical response variable, for example, the home price, we just average the response variables of the closest k observations. When classifying observations, for example, predicting whether a citizen will vote Democratic or Republican, we use majority voting. If the majority of the k closest observations are of one class, then we predict that class. If the majority of the k closest observations voted Republican, then we would predict that this new voter, would vote Republican. Note that the k-nearest neighbors is a little different than the regression approach. We didn't need to minimize a cost function to fit the model because there were no parameters, no theta i's to find. Still, we'll use performance on the development set to determine the best value for k. Then we'll assess the performance of the model on the test set.